Now I would like to share with you the example of the FIR filter design. Example 6.3, design a FIR filter to meet the following specifications. FP equal to 2K, FS equal to 4K, AP equal to 2 dB, AS equal to 40 dB, and sampling frequency S equal to 20 kHz. So first of all, we find the digital passband frequency, that is the FP equal to the FP divided by S. Okay, in the question, FP given is the 2K. So 2K divided by sampling frequency is 20K. So I obtain 0.1. And Fs, okay, capital Fs, that is the digital stopband frequency, equal to Fs divided by S, that is 4K divided by 20K. I obtain 0.2 Hz. Next, I would like to determine which filter require you to design based on the information given. So if I draw a graph, okay, FP equal to 2K, this is the FP, and Fs equal to 4K. So this means that the passband is at 2K, and then Fs means a stop band at 4K. This means that it's like this. Okay, so this is what? This is referred to the low pass filter. So you allow the low frequency to pass, so it's a low pass filter. Next, I would like to find or select a window. From the recipe, we know that the AWS should more than or equal to the AS, and our AWS in the question is 40. The AS in the question given is the 40. And the AWP should be less than AP. And AP in the question given is 2. It's like this. So remember, AWS should more than 40 and AWP should less than 2. Then we go to the table. So from the table, AWS should more than or equal to 40. So only these three windows are meet to the requirements: Bonham, Hemming, and Blackman. Okay, and AWP should less than or equal to 2. So these three also meet the requirement. So we only choose the window which first starting number meet the AWS requirement. Means that this is the first window that starting number meet the AWS requirement. So this one meet the AWS requirement. So we will choose the Bonham. So AWS more than or equal to AS, so it's 44 more than or equal to 40. And whereas AWP should less than or equal to AP, that is 0.1103 less than or equal to 2. Next step is select the N. So FT, the transition width, equal to Fs minus Fp. Fs is 0.2 from the calculation. Okay, Fs from the calculation, and also Fp from the calculation, that is 0.1. So I obtain 0.1. And we go back to the C. And then from the table, you obtain the C equal to 3.21. And Fs minus Fp equal to C over N. Fs minus Fp is equal to 0.1 equal to C is 3.21 divided by N. So N is equal to 32.1. So which is approximately equal to 33. We approximate to a higher number. And then the fifth step is the low pass prototype cutoff frequency. Fc equal to 0.5. FP plus FS. So that is 0.5 multiplied with 0.1 plus 0.2. So I obtain 0.15. And then the impulse response is the Hn equal to 2Fc sin 2nFc. So I obtain 2 times 0.15 multiplied with sin 2 times 0.15 times with n. So I obtain 0.3 sin 0.3n. So for the range of negative 0.5 n minus 1 to 0.5 n minus 1. So this is equivalent to n is equal to 33. Okay, n is equal to 33, which is equal to this one. So minus with 1 is 32. 32 times with 0.5, you get minus 16 to 16. And then after Hn, we obtain the Wn, which is referred to, for the one hand, we obtain 0.5 plus 0.5 cos 2 pi n divided by n minus 1. So this is equivalent to 0.5 plus 0.5 cos 0.0625 pi n. And now you can draw a table. Okay, the table, the n is from minus 16 to positive 16 based on the range. And then you write down the Hn, Wn, and Hwn. Then you calculate each of the value. So you can fill in the value into this table, okay, in which the n is from minus 16 to 16, and you calculate using the calculator for the Hn, Wn, and Hwn. Hwn is simply the Hn multiplied with the Wn. Next, we go to another example. Design an FIR filter to meet the following specification. FP is 4K, Fs is 2K, AP is 2 dB, AS is 40 dB, and sampling frequency S equal to 20 kilohertz. So first of all, we need to find the digital passband, that is the FP divided by S, which is equal to 4K divided by 20, you obtain 0.4. And then Fs equal to the stop band frequency is the Fs divided by S, you have 2K divided by 20K, so you obtain 0.1. And then next you can draw a graph based on the stop band and the pass band. So from the question given, 2K is the start pass band, and then 4K is the stop band. So you can do it like this. So this is the Fs stop band, and then Fp is the pass band. So this is the high pass filter. So next step, we want to select a window. AWS should more than or equal to AS, which is more than 40. And AWP should less than AP, should less than 2. So let's go to the table. So from the table here, AWS should more than or equal to 40. So this is the first one is the one hand. And AWP should less than 2. So this one also less than 2. So therefore we choose the one hand. So AWS is 44 and AWP is 0.1103. And then next step is select the N. Ft, the transition width equal to Fp minus Fs equal to 0.2 minus 0.1, which is equal to 0.1. If you notice that the previous example is the Fs minus Fp. Okay, but this question is FP minus Fs. Why? This is because it doesn't matter either Fp minus Fs or Fs minus Fp. The most important thing is the higher number or bigger number minus with a smaller number. Okay, you will get the positive value. So in this case, the pass bank has a higher number, stop bank is a lower number, so you will get the positive value, that is the 0.1. Therefore, Fp minus Fs is equal to C over N. C is 3.21 divided by N, and N is equal to 32.1, which is approximately 33. Now we can design the high-pass filter in one of the two ways. Okay, first of all, is the Fc equal to 0.5 Fp plus Fs. So 0.5, 0.2 plus 0.1, which is equal to 0.15, and Hn equal to 2Fc sin 2n Fc. So this is equivalent to 2 times 0.15 sin 2n times 0.15. So this is equivalent to 0.3 sin 0.3n. Whereas Wn is referred to 0.5 plus 0.5 cos 2 pi n divided by n minus 1. So this is equivalent to 0.5 plus 0.5 cos 0.0625 n pi. And then we need to calculate the range, which is from minus 0.5 n minus 1 less than n and less than 0.5 n minus 1. So the n is substituted with the 33, so we have 33 minus 1, the 32, multiply with minus 0.5, you get minus 16 up to 16. Okay, once you have the Hn, Wn, next is the Hwn. Hwn is simply Hn multiplied with Wn. And then the high pass n, okay, using the spectral transformation, that is the delta n minus with Hwn. So this is the first method. Okay, the second method is using the Fc equal to 0.5 minus 0.5 Fp plus Fs. So we substitute the value of Fp and Fs, and then we obtain 0.35. And then we want to calculate for the Hn, that is 2Fc sin 2n Fc. This is equivalent to 2 times with 0.35 sin 2 times 0.35 times with n. This is equivalent to 0.7 sin 0.7n. And then Wn is referred to 0.5 plus 0.5 cos 2 pi n divided by n minus 1. This is equivalent to 0.5 plus 0.5 cos 0.0625 n pi. So this means Hwn equal to Hn multiplied with Wn. Okay, and for the spectral transformation, there is the Hpn equal to negative 1 power of n Hwn. Next, you can draw a table to fill in the value. So in the table, you can fill in from the n from minus 16 to 16. You can fill in the Hn, Wn, and Hwn. And then for the transformation, you have the delta n and Hp. So you can do it the same for the first method and the second method, but both first and second methods will get the same result. Lastly, I'll show you another example, that is to design an FIR filter to meet the following specification with the AP equal to 3 dB, stop bank equal to 45 dB, passband is in between 4 to 8 Hz, and stopband is 2 and 12 kHz. So to solve this question, first of all, we need to know the center frequency. The F0 equal to 0.5, 4 plus 8. So this is from the formula, okay? The center frequency at the passband. So 0.5, 4, and 5. So center frequency at the passband is 4 plus 8 divided by 2. So you get 6 kHz. And then the next step, okay, we draw the passband and the stopband. So you have a passband is 4 and 8, stopband is 2 and 12. So you have 2, you have 4, and then you have the 8, 10, 12. Okay, so passband is stopband at 2, passband at 4. So we have like this. And then stopband at 12. This means like this. This is the passband. Stopband at 12. So this is a band pass filter. So if you look at here, you have the 2 kHz here. And if you look at here, this is the 4 kHz. So this means that the specification do not show the arithmetic symmetric. The smallest transition width is 2K. It is 2K only. For the arithmetic symmetric, we therefore need to choose the band edge as 2, 4, 8, and 10. Okay, this means that we will have this one. Okay, we move to here. So we name it as a F1, F2, F3, and F4. So third step is the digital frequency for the passband. Digital frequency for the passband, we have the FP1 divided by S and FP2 divided by S. So this is equivalent to, this means that the passband, okay, passband is 4, right? This is 4. So 4 divided by 25, divided by SS is 25 kilo. So 4 divided by 25, that is, you obtain 0.16. And then another value for the passband is 8. So 8 divided by 25, you get 0.32. And then for the stopband, that is the Fs1 divided by S and Fs2 divided by S. So this means you have the 2, value of 2 here. 2 divided by 25, you get 0.08. And 10 divided by 25, you get 0.4. So you must use the new band edge. And then F0 equal to F0 divided by S, which is 6K divided by 25. The center, F0 is the center frequency at passband, divided by the sampling frequency. So you obtain 0.24. The next step, okay, is the low pass band edge become the FP equal to 0.5, FP2 minus FP1. Okay, so this means it's 0.32 minus 0.16 divided by 2, and you obtain 0.08. And then the band edge for the stop band, the Fs equal to 0.5, Fs2 minus Fs1. So this is equal to 0.4 minus 0.08 divided by 2, which is equal to 0.16 for the stop band edge. Next, we would like to choose for the window. Okay, so AWS must more than the AS. AS from the question given, it should be more than 45 dB. And for the AWP should less than AP. And AP given is 3 dB. Now let's go to the table. If you look at here, AWS should more than AS. Okay, AS should be 45, means that should more than 45. AWS should more than 45. So this is the first one. And then the AWP should less than AP. So AWP should less than 3 dB. Now this one is mid, so we choose the Hamming. So this one is, the value is 0.0384, and for AWS is 53. Now we select the N, the FT equal to the FS minus FP. Okay, FS has a higher number, so 0.16 minus 0.08, which is equal to 0.08. And then Fs minus Fp equal to C over N. This is 0.08 equal to C is 3.47 from the table, divided by N. N is equal to 43.375, which is equivalent to 44N. Okay, after you find the N, you find the cutoff frequency. That is the Fc equal to 0.5, Fp plus Fs. So 0.5, Fp is 0.08 from the calculation. And then Fs is 0.16. This is equal to 0.12. And next we can calculate the low pass impulse response is the hash N equal to 2Fc sin 2N Fc. So this is equal to 2 times 0.12 sin 2 times 0.12 times with N. So this is equivalent to 0.24 sin 0.24N. And then for the Wn, we have 0.54 plus 0.46 cos 2n pi divided by n minus 1. And this is equivalent to 0.54 plus 0.46 cos 0.0465 n pi. So HWN is simply Hn multiplied with Wn. And the hash bandpass N equal to 2 cos 2 pi NW NF naught HWN equivalent to 2 cos 0.48 pi N HWN. And then don't forget, we have to calculate the range. For the N is negative 0.5, N minus 1, and then from 0.5, N minus 1. So N from the question given, you calculate N is equal to 44. So 44 minus 1 is 43. 43 times with negative 0.5 to obtain negative 21.5 up to 21.5. So this is the range. And next you can draw a table. Okay, the N is from negative 21.5. So means the each increment is 1. So negative 20.5 and negative 19.5 up to 21.5. So you calculate for each one. So Hn, Wn, HWN, and also the 2 cos 0.48 pi n and HBP. What's the value? So this is considered complete. That's how you solve each question, okay, based on the procedure. So that's all for the example of the FIR filter. Hope you can understand. Okay, thank you for watching class. Bye.